Hi everyone, how are you? Hope you are doing good. So what you are looking at is a live structure analysis tool. I built this interactive beam calculator to help visualize what's actually happening inside a simply supported beam when we apply both a uniform distributed load and point load at the same time. Every time you move a slider, the bending moment diagram, shear force diagram, and the deflected shape update instantly. So let's talk about the beam setup first. So here is the beam. It's a simply supported, meaning it's rests on a pin at point A at the left and the roller at point B on the right. So as we know, the pin prevents both horizontal and vertical movement, while the roller only prevents vertical movement. Together, they make the beam statically determinate, which means we can solve everything just using an equilibrium equation, like sum of vertical force, sum of horizontal force, and the sum of moment equals 0. So now let's talk about the loads that we have on this beam. So we have two loads. One is distributed load of W and other is the point load of 100 kilonewton. So on the left side, we have got five sliders, UDL, intensity, the point load, and the position of that point load expressed as a fraction of the span, which means the value here 0.5 means the center of the beam. And if we change this value, then our load will change automatically. So now let's see or let's watch what happens when I shift the point load closer to the B. So the reaction at B goes up and the reaction at A drops. Like we can also see, right? If I move towards the B, then the reaction at point A is 87, 85, 80. So as we move towards the right, the reaction at A goes down. So and the reaction at B will goes up. So the reactions are calculated using moment equilibrium. When the point load is right in the middle, A equals B, and both reactions are equal, which makes perfect sense. For example, if we put this point load just in the middle, like at 0.5, our both reaction at point A and point B equals 110 kilonewton, which makes perfect sense. So now let's talk about the bending moment diagram. So this blue area is a bending moment diagram and it tells you how much bending is happening at every point along the beam. With only the UDL, the shape is a smooth parabola. So now let's check. If we make the point load value 0 and it means the beam only UDL is acting on this beam. So which means our the bending moment diagram is parabola and the maximum bending moment diagram is 90 kilonewton meter in this orientation. So now watch what happens when I add the point load. So when I add the point load, see that kink, that's the signature of the concentrated load. It introduced a sudden change in slope because of the shear force jumps at that point. The number at the peak is Mmax, which is in kilonewton meter, and this is the critical value in beam design. Your beam section has to be able to resist this moment, otherwise it fails. Notice how moving the point load away from the center shifts where the peak occurs and it also changes its magnitude. The tool tracks that automatically and you can see it update in the results cards on the left. Now let's talk about the shear force diagram, which is in the green one. The shear force represents the internal force the beam cross section has to resist, the tendency of one part of the beam to slide vertically past the other. With just a UDL, it starts positive at A and drops linearly to negative B. And at A is 60 kilonewtons and at point B is negative 60 kilonewtons, which is equals. And this is the case for only UDL. Linear drops because the load is uniform. Each extra millimeter of the beam adds a little more load and reduces the shear a little more. So now let's add the point load. See that vertical jump over here? That's the concentrated force P causing an instantaneous change in shear at that exact location. Where the shear line crosses 0, that's where the bending moment is at its maximum. And you can see that the crossover point shift as I move the load. The two diagrams are always telling the same story from different perspectives. Now let's talk about the deflected shape. The red dashed curve is the deflected shape, what the beam physically looks like under load. The maximum deflection delta is shown in results curve. Watch what happens when I reduce EI. So look, when I reduce the EI, the value of deflected shape goes up. It means the beam gets softer and sags more. Increase it and deflection shrinks. In practice, EI is your main tool for controlling how much the beam bends. Choose a deeper section or stiffer material or both. And that's the full pictures. Reaction, bending moment diagram, shear force and the deflection all connected with each other. And if you have ever sketched bending moment diagram and shear force diagram by hand and wanted to double check your intuition in a real time, this kind of tool is exactly for that. And I'm planning to add fixed in beams and cantilever beams and beam frame. So if that's something you would find useful in future, drop a comment or follow along. I post projects like this regularly from now on. Thank you. Thank you for watching.